So first of all, I realized there was a confusion with the assignment. It said Thursday, February 28th. What have you interpreted it to be? Feb 28th or tomorrow? Huh? Or Moodle had a separate deadline?
No, it's others like it is 28th.
I see. So the Moodle, Manish puts a separate deadline. What? Because on top of the assignment, I had by mistake written Thursday, February 20th. But when it's uploaded on Moodle, is there a deadline with it? I don't know how Moodle works because I'm not an instructor.
Deadline is 12 AM at 20.
I see. Okay, fine. So it was okay. So I just sent assignment 3, so that should also go up. So that will be due next week. Yeah. Okay. We are running a little behind with the assignments than where we are the lectures. So I want to catch up. So hopefully by next time, maybe after one more week, we'll have caught up. Yeah. Okay, good. So last time we discussed the issue of once again, actually attendance is low, and I'm not sure why. Not even all the registered students are here, right? So I don't know if some of you are watching this. But if you are, this is not supposed to be a recorded course, so please come to the lectures physically. Okay, so last time we discussed the question of the potential. Now we want to go on and discuss a different concept, which is a concept of crossing symmetry. Are there any questions from last time? No. Okay. Okay. So today I want to discuss the issue of crossing, which we discussed last time. We discussed this a little bit in our lecture, in the beginning of last lecture, but then we didn't complete it. And so I want to now explain what this point is. Okay. The first point about crossing symmetry is that crossing symmetry is not a symmetry in the sense of symmetries that we looked at earlier, where we looked at Noether's theorem and we looked at charges and conserved balance. Okay. It's the fact that some processes which have some kinds of incoming and outgoing particles, their amplitude might be related to a different process where some of the incoming particles become outgoing and some of the outgoing particles become incoming. Okay. So it's the fact that sometimes you can do various transformations to a Feynman diagram, and you will find that the amplitude remains invariant or it transforms in a simple way. And so crossing symmetry is really a statement of this property of Feynman diagrams. Okay, good. So let me give you the simplest example, and that's the following. Okay. Let's say we look at this diagram, right? This is the basic vertex in what we call model 3. Okay, what is the physical interpretation of this vertex? Huh? Yeah, okay, so that's one possibility, right? That you have some, you have one of these nucleons, they come in, they emit a meson, and they keep going. I'm not even sure what you said, but that's one possibility. Okay, good. But that's not the only possibility, because you could also interpret it as a nucleon. So let's write. So one is that nucleon emits a meson, right? But then there's another possibility, which is nucleon antinucleon plus antinucleon is a meson. That's this possibility. So this possibility A is this one, right? This possibility A. But there's a different possibility which has to do with just labeling the momenta differently, and that is that this is possibility B. Okay. But there are other possibilities. For instance, one possibility is meson decays to nucleon plus antinucleon, right? Okay, this is possibility C. even other possibilities, right? In fact, there are 8 possibilities. I won't write all of them. Meson plus this possibility D, which is meson plus nucleon. So nucleon absorbs a meson. So it could be emitting a meson, it could be absorbing a meson, and so on. And in fact, for each leg, you can flip the sign of the incoming momenta to be outgoing, and you'll get a valid process. Okay. Maybe the process where all 3 are outgoing clearly doesn't make sense, because it suggests that something emerged from nothing, and the process where all 3 are incoming also doesn't make sense. Okay. But every other possibility, there are 6 other possibilities. I think we missed 2, but doesn't matter. Yeah, which will give you a valid process. So, but however, the important point is that the Feynman diagrams always assign the amplitude minus Ig to this, right? What changes is just the sign of what momenta go into the delta function. So here, you would write, we're using Ig, right? You'd write Ig, and then you'd write 2 pi to the 4th, you'd write delta 4, and here you would write K1 minus K2 minus K3, right? And so for this also you would write something similar. You would write minus Ig 2 pi to the 4th times delta 4. But here you would write K1 plus K2 minus K3, and so on, right? So for every amplitude, you would basically write the same numerical factor, which would be minus Ig, right? And then you would multiply it with a delta function where the signs of the momenta were slightly different in the different cases. Okay, this is what it was to be. Once again, I'm thinking always of K1 as the top, K2 and K3. For C also, you would do the same thing, except here you would write minus Ig times 2 pi to the 4th times delta 4 of K3 minus K1 minus K2. And then here you would write G K1 plus K2 minus K3. Okay. So all that's happening is that the 4 momenta that goes in here is getting flipped, right? But other than that, the Feynman diagram is basically attaching the same value to all of these different processes. Okay. So you see, it's kind of it's clearly kind of redundant to think of these processes differently, right? Because the Feynman diagram is telling you that all these processes are clearly related because they have the same amplitude, right? And so if only we had a more compact notation, we could represent all of these processes in a single diagram. Okay? And the compact notation is this, simple thing you can do is we just mark all momenta as incoming. Okay. Now you might say, how can you do that? How can you mark all momenta as incoming? But we have just 1 second. Did I want to say? Yeah. But this is fine to mark all momenta as incoming, because all of these momenta have a particular property, right? And what is the property that so mark all external momenta? And the property they have is that they all satisfy Ki squared, okay, is equal to either m squared or mu squared, depending on what particle there is, right? And there is something else about them which is special, which is that they all have that's because all the external particles have to have positive energy. Right? There's no notion of an external particle that has negative energy. Okay, so all the external momenta have the property that they all have positive energy and they are on mass shell, And the fact that they're on mass shell is important, right? Because if they were not on mass shell, then the notion of whether they had positive energy or negative energy would not be a Lorentz invariant notion. So the fact that the zero component is positive is a Lorentz invariant statement. It holds true in all Lorentz frames, and it has to do with the fact that the energy of all external states is positive, right? Okay. Okay, good. So, if we mark all the external momenta as incoming, what will happen, right? What will happen is that some of the momenta that we have will end up having the wrong sign for ki0. So when we mark all incoming momenta as in, right? Some momenta might have and what happens when we encounter something like this? Well, we just recognize that the physical particle actually is outgoing. Okay, and this means so it's consistent to mark all momenta as ingoing, and the reason it's consistent to mark all momenta as ingoing is that it can never cause any confusion. You mark all the momenta as ingoing, okay, and you might find that some momenta have ki0 smaller than 0, okay, but that can't be physical because the physical momenta all have ki square equal to m square and ki0 greater than 0. So whenever you encounter a momentum which has ki0 smaller than 0, you just interpret that as an outgoing particle which you marked as incoming. Something is burning. Somebody burned some JCB here, I think. You guys don't know? There's a crowd outside. There's some, maybe switch on the AC. There's someone, I think there's some road building equipment which someone has burnt it. Switch on the AC. You guys want to switch this on? Oh, these ones are different from this. Oh, can you switch those on, please? There's a really strong burning smell. Huh? You don't have the burning smell? Really? Oh, it's pretty strong, right? There is actually a fire. There's a fire truck outside. Because how? Maybe you think I saw the fire truck, so I'm imagining it's I don't think so. No, it could be, but oh man. If you know how to switch this on, try. Maybe it takes time to come on or something, right? This one seems to be red. At least it's not blinking orange. Let's try this. Good. And now we try this one also. Maybe it needs time. Okay, we'll give it some time and then we'll start. Okay. Anyway, yeah. So yeah. So crossing has to do with the fact that the same Feynman diagram can be used to represent different processes, as we just said here. And one way to take advantage of this and avoid the redundancy, avoid having to write 6 different diagrams, is to simply mark all the external momenta as incoming. If you do that, then what is the amplitude that you would write down for this? The amplitude you would write down for this would simply be, with this convention, the amplitude would always be for all processes. That's it. Okay. So the amplitude is always minus Ig times 2 pi to the 4 times delta of the sum of the momenta. Okay. What we said right now, I said in the case of a 3 vertex, and you might worry that maybe this is never represents really a physical process, since as I said, in these cases you don't have, it's very hard to satisfy energy momentum conservation. But the same phenomena that I said is also true if you consider other more complicated diagrams. Right? Right? So exactly the same thing is true here, right? We could start playing the same game here, where we mark these momenta as K1, K2, and K3 and K4. That's one marking, right? And that is that nucleon plus anti-nucleon goes to n plus n bar. And you'd write down some amplitude for that. The amplitude you would write down would be minus Ig, would mark this P, K1 plus K2, right? And so you'd write down some amplitude for that, which would look like minus Ig squared by K1 plus K2 squared minus M squared. I'm just writing down one diagram. Okay, remember this process has another diagram as well, which I'm not drawing. Okay. I'm just pointing out that the same phenomena also occurs at higher points. However, you could have interpreted this process in a different way just by marking the momenta differently, right? You could have said, well, I want to think of this process in a different way. Maybe I want to think of it as, a nucleon, 2 nucleons coming in and scattering, right? So if you wanted to do that, then what you would do is you would flip the sign of this. So here's another interpretation of the same diagram, right? Which is you just change the direction of how you mark the arrows. Okay. And now it looks like n plus n goes to n plus n. And of course, the answer that you have is the same, right? It's not like the answer is different. But what is the answer? The answer would just be by K1 minus K2 squared minus M squared. I mean, it's not the same, but it's related by crossing in this way. Right? So, you have these two processes which are represented by the same diagram. However, just based on how you label the momenta, whether you label them to be incoming or outgoing, the physical interpretation of the processes can be very different, right? But we don't really want to do this, right? We don't want to be, we want to take advantage of the fact that the same diagram can represent all these processes. Therefore, in the new convention, what would we do? Well, we'd mark all the momenta to be incoming. Right? So we'd still draw this diagram. right? And we write the amplitude to be minus ig squared by k1 plus k2 squared minus m squared. Okay. Now in this diagram, you can read this diagram as n plus n bar goes to n plus n bar, or you can read this diagram as n plus n goes to n plus n, or you can in fact read this diagram also as n bar plus n bar goes to n bar plus n bar. Okay. If you wanted to read this diagram as n bar plus n bar goes to n bar plus n bar, what are the momenta, so you'd have to take k2 0 to be positive, k4 0 to be positive, k3 0 to be negative, and k1 0 to be negative. If you did that, then the same diagram would also be able to represent n bar plus n bar goes to n bar plus n bar. Okay. So this is an example of crossing, which is the fact that some amplitudes with some particles going in and out are related to other amplitudes where some of the ingoing particles have been replaced by outgoing particles. Okay. And this new convention that we have helps us make this symmetry manifest, because it doesn't rely on on the fact that it makes it manifest because the value you get for the Feynman diagram doesn't rely on which of these different interpretations that you choose. Okay. Okay, so crossing is the notion of crossing clear, and how our new convention helps make this manifest? So last time there were some questions about this that I postponed to this time. But this is a good time to ask those questions if you have. Okay, let's just do some diagrams. Let's do some processes just to be comfortable with this new notation. We already did this one. There's of course another process that's related to this one. There's another diagram here, which is I can do this by just interchanging this. What's the best way to try it? Maybe I can just do it by interchanging this. Give me this. Yeah. I'm just trying. Yeah. So I'm just thinking of what the best way to do it is. I think maybe I can just interchange these guys, right? K1, mark this as K2, and then I can make another line come here. Sorry, 1 second. I want to mark this as K4, and I want to mark this as K2. Okay, so this is the other process that we have, where I mark this as K4. Okay, but however, in this process, the amplitude for this process is minus Ig squared into K1 plus K4 squared minus m squared times 2 pi to the 4 times delta 4 of K1 plus K2 plus K3 plus K4. Okay. Okay. So this is the other diagram, which you can draw in different ways. But you can think of this as taking those top two particles and crossing the lines, because those two particles are identical, so I can interchange them. Or you can think of this in other ways. But this is the other diagram that we have. And these two diagrams now you can represent in many different ways. Okay. So for instance, you can think of them as we are discussing as nucleon and antinucleon going to nucleon and antinucleon, or you can think of them as two nucleons scattering off each other, or you can think of them as two antinucleons scattering off each other. Okay? So the same set of diagrams can represent many different processes. Okay? It represents, so the full amplitude is the sum of these two, and same diagrams represent n plus n bar goes to n plus n bar, or n plus n goes to n plus n, or n bar plus n bar goes to n bar plus n bar. Okay. So we have these different processes that are physically distinct, okay, but they're all given by just summing these two diagrams. Okay. Okay. And if you go back and you look at, I think we looked at maybe these different processes where we looked at n plus n bar goes to n plus n bar, okay, and then we looked at n plus n goes to n plus n, okay. And when we when we are drawing those diagrams, we drew the diagrams slightly differently. But in fact, the basic diagrams that you have are really the same diagrams, and if you just turn them on the side, or you turn them some other way and mark the momenta correctly, you will see you get back the diagrams that we had previously.
These two cases
Huh.
to end by which external states are same as internal states.
External states are?
And
Yes. Yes. Yes.
The same diagram we were just
That's right.
But in the
Yes.
two diagrams, but the second diagram was different.
We had, in which case did we have different diagrams? N bar going to n bar. So let's try and draw the diagrams. Yeah. Yeah. So let's draw the diagrams in the old convention. So let me draw this diagram here in the new convention, and then we'll draw this in the old convention so we can see how it's the same. Yeah. Okay, so this is one diagram, and the other diagram we have is the same one. How's I marking this? K4 on top. Okay, and this one gave you minus Ig squared by K1 plus K2 squared. Okay, so these are the diagrams that we have, and I claim these diagrams you can represent to, you can use to get everything. Okay, so let's look at let's draw these diagrams in the for all the processes in differently. Okay, so you can see how it comes out to be the same. One of the processes got hidden, but that's okay. Okay, so now I'm going to draw the same diagrams in the old convention. Okay, so you want to see which one, the n plus n bar goes to n plus n bar. Okay, so so this was K1, K2, K4. Okay, and here we would have written this as minus Ig squared by K1 plus K2 squared minus m squared, okay, times 2 pi to the 4 and delta 4 K1 plus K2 minus K3 minus K4. Okay, and the other diagram we drew was this one, I think. Have to reverse it. This is right. Did I write it correctly? No, I have mislabeled the momenta, right? I should have put K4 here, right? No, I want to mark, I'm marking this as incoming, but I think I mislabeled the one which was outgoing. I should have labeled this as K4 and this is K3. The incoming nucleon I want to mark as K1, the incoming antinucleon as K2, the outgoing nucleon I want to mark as K4, and wait a second. Oh, sorry. Okay, I should have used, yeah, sorry. So let's call this K4. Now the outgoing nucleon is K4 and the outgoing antinucleon is K3. Yeah, okay, good. So good. So you see, this one looks like, this diagram looks like minus Ig squared by K1, in this case minus K4 squared minus m squared. But if you look at what this diagram does, there you have K1 plus K4 squared, but you see if you replace K4 with minus K4, you'll get back exactly this diagram. So you see here we had two diagrams in the old convention. One diagram read like K1 plus K2 squared, which is this diagram. Okay. The other diagram is the same as this diagram. I've just drawn it differently. It's really the same as this diagram because you see what's happening is, K1 and K4 are meeting at a point. K1 and K4 are meeting at a point. I kind of just drew it differently just to keep K4 on that side. But those legs are crossed, right? So the important thing about the diagram is which momenta are meeting. So K1 and K4 are meeting at a point, and K2 and K3 are meeting at a point. Yeah. And so you see you get K1 plus K4 squared. Here you get K1 minus K4 squared, but that just has to do with flipping the momenta, right? Remember when you mark the momenta as incoming, that you have to mark the momenta as K1 minus K4. Okay, so you get the same set of diagrams, and that's also true here. And indeed, this might be something which is confusing, right? Because how did we justify the cross diagram? We justified the cross diagram by saying, well, the external particles are identical, and therefore, if you draw one, you have to draw the other. Okay. However, crossing tells us that these are the only two diagrams, and they have to contribute. Sometimes, you might look at a process where the external particles are not identical, but it's still the same two diagrams that contribute. That's why it's it's a powerful property of this formalism that it makes this symmetry manifest. Okay, so this is something which is manifest in quantum field theory. And quantum field theory tells us that these different processes are related to one another. Okay. So in the n plus n bar going to n plus n bar, you might have thought that Bose statistics was not really important, right? But in fact, it is secretly important because this process is related by crossing to a different process, which is n plus n goes to n plus n, where Bose statistics is important. Okay. Of course, all this is packaged into quantum field theory. If you didn't think about all of this and you just sat down and drew the diagrams by brute force, you would get all the right answers. Right? But it's important to realize that some of these things are all related, and that's why the formalism of quantum field theory is so rigid.
You are not audible. Hey, uh, yeah, I think the ICT's Zoom is muted. Yes, we cannot hear you. It is showing that the ICT's host is muted. So
Hi, can you hear me now?
Yeah, now we can hear you.
Okay, fine. Okay. And it just got muted recently, or it was muted throughout?
No, I think the ICTS Zoom lost connection for a minute, and then when it came back, it was automatically
I see.
muted.
Okay, fine. Thanks. Okay, great. Okay, good. So I wanted to discuss this other process, which was n plus n bar goes to 2 phi, and that process is this one. And of course, because of Bose statistics, we should consider a different process. I mean, a different diagram where you cross the lines. Okay, and let me label this to be K1, K2, K3, K4, K1, K2, K3, K4. And this diagram has some amplitude which looks like minus Ig squared by K1 plus K4 squared, but minus mu squared, okay, because the propagator that runs here has mass mu. Okay. So this is the process for n plus n goes to 2 phi. If you interpret this with K3 and K4 having negative signs of K3 0, okay, and K1 and K2 having positive signs of K3 0. Okay. Of course, this process you can also think of as once again this elucidates the same point that I described recently. You can also think of this process as n plus phi going to n plus phi. And if you thought of it that way, then you would take K1 and K4 to be positive, and you would take K2 and K3 to have negative momentum, okay, to have negative signs of energy. And now if you did that, you might once again be confused why you're drawing the cross diagram. But of course, if you went back to the old convention, you would draw these diagrams even there, okay, in the same way that you're drawing them here. Okay. So this process can also represent n plus phi going to n plus phi, n bar plus phi going to n bar plus phi, or in fact also 2 phi going to n plus n bar. That's also perfectly valid. Okay, so there are different possibilities, but they're all represented by the same two diagrams. Okay, and they're all related by crossing to each other. Okay, good. So are there any questions about this? Okay, good. Then I want to discuss now a slightly different kinematic representation of variables that also helps in this discussion of crossing. And is also useful for many other purposes. Okay. Notice, in the diagrams that we've been getting there, we always have these kinds of combinations like K1 plus K2 squared, K1 plus K4 squared, and so on. Okay. So in a 4-point process, there's some names that we give to these variables, and they're called Mandelstam variables. Okay. Okay, all incoming. And the names that are given to them sometimes are that S is called K1 plus K2 squared. Okay. T is K1 plus K3 squared, and U is K1 plus K4 squared. Okay. These are just some names that people give, and these names are used especially in the case of 4-point processes. I'll describe in a few minutes what happens when you have more general processes, okay, n-point processes. Okay. Notice first that these are all Lorentz invariant. And not only are they Lorentz invariant, these are basically the only Lorentz invariants you can make. Can you think of some other Lorentz invariant? In a scalar theory, if you had vectors or something else, you might sometimes be able to make additional Lorentz invariants by contracting some of the momenta with external polarization vectors. But in the theory of scalars, notice these are the only Lorentz invariants you can make. Can you think of some others? No? Okay, can you just name some others? What other Lorentz invariants are there? Even if they're related to this, can you just list some other Lorentz invariants? So it's not a trick question, just some quantities are Lorentz invariant here. Yes, any other combination? There are no other combinations you can get by looking at K1 plus K2 squared, but for instance, you might have thought that K1 square is the Lorentz invariant, but it's not really a Lorentz invariant because it's fixed to be the square of the external mass. Okay. So it's just a number. It doesn't tell you anything about the process. You might have thought K1 dot K2 was a Lorentz invariant, but in fact, this is just S minus K1 squared minus K2 squared. Just for the process of, just for this discussion, let me take all the masses to be equal. You can do this with equal. Let me take Ki squared equal to M squared, just for purpose of simplicity. In which case, this just becomes S minus 2M squared by 2. Okay. So what other Lorentz invariant can you write down? Well, you could have written down K1 dot K3, but it's the same thing with T, or K1 dot K4. Or you could have written down, now you might have said, let me write down K2 plus K3 squared. Right? But K2 plus K3 squared is equal to K1 plus K4 squared by energy momentum conservation, right? And therefore, K3 dot K4 also you can write in terms of, K2 dot K3 also you can write in terms of K1 dot K4. So you might have said, let me write down K2 dot K3. Okay. But K2 dot K3 is again the same thing, right? It's just U minus 2M squared by 2. Yeah. So every Lorentz invariant you can make here with these momenta is related to this ST and U. So and therefore, it's not surprising that all the amplitudes that you write down can only be related to ST and U. They're only functions of these Mandelstam variables. Okay. Okay. However, these variables are not all independent, as I now want to show you. Okay. they're not all independent, and that's easy to see. Okay? It requires a little bit of algebra, but it's easy to see. Right? One way to see it is the following. Okay? Let's look at twice s plus t plus u. So this looks like k1 plus k2 squared plus k1 plus k3 squared plus k1 plus k4 squared. And then in the next representation, let me write the other, I wrote this as k1 plus k2 square, k1 plus k3 square, k1 plus k4 squared. Okay? But I could also have written this as k3 plus k4 squared. I'm just writing it. I'm just making it up. I'm just writing down an identity. So I want to show you that the variables are not independent, and I'm just choosing to write it with a 2. This is just an identity. Plus, this is not the only way you can prove the identity. It just requires some algebra, but it's one convenient way to prove it. Okay. What did I do here? S plus t plus u is k1 plus k2 square plus k1 plus k3 square plus k1 plus k4 square by definition. However, k1 plus k2 square is also k3 plus k4 square because k1 plus k2 is k3 plus k4. So, twice s is k1 plus k2 square plus k3 plus k4 squared. And same for twice t and twice u. Okay. Okay. Good. Now, if you add this up, you will find, you get k1 squared, you get k1 squared, and you get k1 squared 3 times, right? So you get thrice k1 squared. But in fact, this guy is completely symmetric in k1, k2, k3. You can check, you also get thrice k2 squared. You get k2 squared plus k2 squared plus k2 squared. Okay. Same for k3 squared. Okay. What about the products of the momenta that you get? Well, you get k1 dot k2 from here. From here, you get twice k1 dot k3. From here, you get twice k1 dot k4. Okay. And similarly, okay. But you never get any other k1 dot k2 from any of the other terms. So you get plus twice k1 dot k2 plus twice k1 dot k3 plus twice k1 dot k4 plus twice k2 dot k3 plus twice k2 dot k4 plus twice k3 dot k4. Okay. 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 However, let me note the following identity. Okay. Note that k1 plus k2 plus k3 plus k4. What is this? This is, it's 0, right? So its square is also 0 because its momentum is 0, right? But this is equal to k1 squared plus k2 squared plus k3 squared plus k4 squared, okay, plus the same thing that appears there, plus twice, I won't write it again, ki dot kj, okay. This just comes from expanding this guy, taking the whole square of this. Okay, you see this? Right? Okay, good. Now, therefore, this twice k2 dot k, this thing that appears here is, there should be, yeah. Okay. Therefore, this thing that appears here, this twice ki dot kj, is in fact the same as minus of k1 square plus k2 square plus k3 square plus k4 square, right? Therefore, this object here is in fact just equal to twice of k1 squared plus k2 squared plus k3 squared plus k4 squared. And what is this guy? It's just twice of mi squared. MIs are these masses of the external particles. So what does that tell you? What we have proved is that S plus T plus U is equal to sum of mi squared. It didn't matter for this that the particles have the same mass or they have different masses. It's always true that S plus T plus U is sum of mi squared. Okay. Okay, this is not the only way to prove the identity. There are many ways to prove it, but it's one convenient way to prove it. Okay, so you see that these different Lorentz invariants are not really independent Lorentz invariants. They are the only invariants that occur. but they're related by a constraint. The constraint is this constraint that tells you that S plus T plus U is the same as sum of Mi squared. Okay. Okay. The different amplitudes that we were finding can all be written as 1 by S minus M square, 1 by T minus M square, and so on. You remember that? For instance, the diagrams that we just drew, depending on how you mark the momenta, I think I marked them this way last time, right? K3, K4, right? And this corresponded to minus Ig squared by K1 plus K4 squared. So as U minus mu squared. Okay. What about the other diagram that we had? Well, that just corresponded to putting K4 here and putting K3 here, right? Just crossing the legs. If you cross the legs, then that just gives you the other diagram was. And that was just K1 plus K3 squared. So the other diagram was minus Ig squared by T minus M squared. Okay. So these diagrams are related, and they all involve only this ST and U. Okay. Of course, whether they involve ST and U depends a little bit on how I label things. I could have chosen to label this to be K2 if I wanted to think of N plus, and then I would have said this was S rather than T and U. Okay. Okay, is this clear? Okay, excellent. So are there any questions about these Mandelstam variables? Okay. Yeah, so I'm just coming to that. So indeed, Mandelstam variables make sense for higher point correlation functions as well. However, they become a little more complicated sometimes, as I will just. For higher point correlators, the definition of Mandelstam variables is not so standardized. For 4-point correlation functions, these are kind of standard names that are used. For higher point correlators, different people use different kinds of names. One convention is we take Sij to be Ki dot Kj. This is not the unique convention. Of course, you could have put twice Sij and added Mi squared and Mj squared, and you would have got Ki plus Kj squared. Okay, but this is really the same information as what we are calling S. Okay, earlier. Okay. Now, however, it's indeed true that if you use this set of all Sij, then this gives you the set of all possible Lorentz invariants there are in the problem. So if you have a scalar particle, if you have a scalar scattering process, then in fact, these are the only possible Lorentz invariants that can appear. There's no other Lorentz invariant that can appear. Okay? And so it is true that whatever process you have can only depend on this Sij. Can't depend on anything else. Okay? But there are some constraints that you get on these Sijs, okay, that go beyond the constraints that we found here. Okay. So And in fact, no one has ever found a way to make these. Beyond those, notice the constraint that we just found above was basically a constraint that told us that sum of ki was 0. If I had written instead of s plus t plus u, if I had written ki dot kj, then this constraint that we had would have been obvious, right? It tells you k1 dot k2 plus k1 dot k3 plus k1 dot k4 plus k1 dot k1 is equal to 0. Okay, is equal to. And so, this constraint that we found in st and u was basically a representation of total energy momentum conservation and the fact that the different momenta were on mass shells. Here, you might get more constraints beyond the ones that come from total energy momentum conservation. So I now want to tell you what these additional constraints are. Okay. First, is it clear that even for higher point correlators, you can define these Mandelstam-like variables? And if you define them symmetrically, they are subject to some constraints, obvious constraints, that come from the fact that sum of ki is 0. Okay. The obvious constraint is just that sum over j, Sij. Stroke is terrible. Color. Okay, so we haven't defined Si for Sii. Okay, so we know that mi squared is equal to 0, right? This is just true because sum of Sij gives you ki dot kj. Okay, you sum over all j except for j equal to I. You add to it ki squared, and that is equal to 0, right? Because sum of ki is 0. So there's some obvious sets of constraints that you get in these Mandelstam variables. This is in fact the same constraint we found there, because there these variables we defined were S1, 2, they are the information of S1, 2, S1, 3, and S1, 4. Okay. And S1, 2 plus S1, 3 plus S1, 4 plus K1 plus M1 square was 0, was the constraint that we had. Okay, okay, good. Now, we might get additional constraints on these Sij that come beyond this. Okay, and here's one way to see it. So how do we know that such additional constraints must exist? First, is it clear what the definition of the variables are and what the obvious constraints are? Okay, the additional constraints I'm about to speak of are like non-obvious constraints, and they're the following. You see, let's drop Snj, okay, since Kn is equal to minus sum of Ki. Okay, so let's drop all of these guys. How many additional Sij are we left with? Two to the no, much smaller. It's just n minus 1 C2. Because you can pick I in n minus 1 ways, because we're not picking I to be n. And you can pick j in n minus 2 ways. Okay. But there's a symmetry because Sij is Sji. So we are left with is it clear why you're left with so many variables? Right? Because you dropped Snj because I said, I don't need to know what Snj is because Kn is the same as minus Ki, right? So if I know all the Sij for K1 to Kn, with Ij all less than n, then I know also what Kn is. You see that? So these variables with S and J are all dependent on the others. If one of the indices is J, is that clear? So I can consider only the indices where I and J are both between 1 to n minus 1. How many such ones are there? I can pick I in n minus 1 ways. I can pick j in n minus 2 ways, but Sij is equal to Sji by symmetry. Therefore, I have n minus 1 by n minus 2 by 2 possibilities. I equals j is trivial because that's ki squared. That's mass shell. Okay, that's just mi squared. That doesn't give you any kinematic data about the scattering process. So is this clear that you have these possibilities? Yeah. Okay, good. Now, we know that there's at least one other condition, which is that on these guys, which is that sum of ki squared what is this equal to? Right, so it's equal to mn squared, right? Okay. Now sum of ki I equal to 1 to n, you can in fact write in terms of these Mandelstam variables, right? The other ones that we have remaining. Because what is it? It's like k1 square plus k2 square plus k3 square plus twice of all of these guys, right? Okay. So that puts at least one more constraint on these different guys, on these different variables. Do you see that? Okay. We have is this clear? You see, we had first n minus 1 by n minus 2 by 2 variables after taking account that kn was sum of ki. But it's not sufficient to just say kn is sum of ki. You also have to impose the fact that kn square has to be mn squared. So I can't just choose k1 to kn minus 1 arbitrarily. If I choose it arbitrarily and I set kn to be minus of that, I'll satisfy energy momentum conservation, but I won't satisfy the mass shell condition. So when I choose k1 to kn minus 1, I have to make sure that whatever momenta I choose have the property that sum of square is equal to mn squared. Okay. This is just equal to sum of ki squared plus twice, of I smaller than j ki dot kj. Right. So this is just equal to sum of mi squared plus twice Sij. Okay. Okay. So this tells you there's an additional constraint on these variables. You can't specify them independently. But now you might have thought you're done. You can just specify all these variables independently, right? Is this really true that you can do this? Can you think of why you might not be able to do this? Like what might stop you from doing this? You see, how many momenta do you have in the game? N momenta, right? How many degrees of freedom does each momentum have? 4, but there's a mass shell condition. So actually 3. Okay. In d dimensions, okay, it has d minus each momenta has d minus 1 independent variables, right? Independent degrees of freedom, right? So how many total degrees of freedom do you have? Forgetting about energy momentum conservation, right? N into d minus 1. And then you have to impose this additional constraint that there's some d delta function. So let's put that as well. It doesn't matter what the exact counting is. Notice that the scaling with n is different. Here you have n squared variables, and there you have a growth that's linear in n. Okay. So if I take n equal to 100, and I say, oh, I have 10,000 different variables, or whatever number you get from here, right? Then it doesn't make any sense if I say I have 5,000 different variables, because you don't have so many degrees of freedom. Okay. So in fact, if you're in low dimensions, if you're in 3 or 4 dimensions or 5 dimensions, you find that the Mandelstam variables are not all independent, and these constraints are not like the simple constraint we derived above. Okay? There are some complicated nonlinear constraints that come from the fact that the dimensionality of the space is finite. Okay, So this is in fact, in when people study scattering amplitudes, even in the modern literature on scattering amplitudes, this is in fact something that people worry about sometimes. One way to get around this is to think of scattering in high enough dimension, which is to say, we are doing some scattering process. Let's imagine that we are living in a very high dimensional space. Sometimes the details of the scattering don't really depend on the dimension. The propagator might always look like 1 by k squared plus m squared and so on. So at least if you write things in momentum space, it might look like things don't really depend on the dimension. And then you might be able to get away with using these Mandelstam variables and writing things in terms of Mandelstam variables. But you should remember that for high enough point processes, in principle, there are some constraints that come from the finite dimensionality of space. And in fact, this problem, which one might have thought would have been figured out a long time back, has never really been figured out, and no one has really managed to understand what to do with these nonlinear constraints. That's right. So if you want to consider a 10-point process or a 100-point scattering process with 12 points, so you want to make some general statement, then you imagine that maybe you're working in high enough dimension, so that these Mandelstam variables become independent. Basically, the point is that people don't really know how to take account of these constraints, but it's not clear that these constraints, treating the Mandelstam variables as independent, seems to have any substantive bearing on the form that scattering amplitudes take. For all effects and purposes, many times people do write scattering amplitudes as if all the Mandelstam variables are independent, although you should remember they're not really independent. Okay. Yeah. No, 1 second. Let me say what I'm saying a little more clearly. Okay. Let me just summarize, and then you can ask the question. Okay. The first point I want to make is that for higher point correlators, you can define these Mandelstam variables. They are subject to some constraints that come from sum of ki equal to 0, okay? And they are subject to the Marshall condition, which gives you some constraints on Snj tells you Snj is not independent, and also tells you that there's an additional constraint. So not all of them are independent. Then there are additional complicated constraints that come from the finite dimensionality of space. Those constraints that you get depend on which dimension you're working in. Okay? Often in this, I'm saying something now about more recent work or modern research work in scattering amplitudes. People think about scattering amplitudes, or they think about correlation functions in ADS-CFT and so on. Often people do write answers as if all of these Mandelstam variables were independent. Okay? And that's okay, turns out to be okay, because it turns out these often these additional constraints don't really affect anything. And one way to justify that is to imagine that you're working in high enough dimension. Okay? And scattering and so on does make sense in high enough dimension. You could imagine that you're in a high dimensional space and you are doing scattering in that. But that's the main point I want to make. Just is that even though there are these nonlinear constraints, they're often ignored in practice when people use these Mandelstam variables. Okay, that's all I want to say about this. But what's the question? It's not about. I don't want to get into the discussion of what higher dimensional physics is. Yeah. Okay. Yeah. So you can imagine theoretically there's no problem in imagining a higher dimensional space as well, right? And imagining there's a high dimensional. You can imagine you're in a 2-dimensional theory or a 1-dimensional theory, right? Those are things. You can have scattering in 2 dimensions as well, or scattering in 1 dimension as well. You might have a chain where there's some scattering happening. Or you might have a plane where scattering is happening. No, there's no measurement here. Sorry, the point is not about measurement. The point is if you computed a 20-point scattering amplitude in a 5-4 theory and wrote the answer in terms of Mandelstam variables, there would in fact be constraints which would tell you that the answer can be written in a very different way in terms of Mandelstam variables because you live in finite dimension space-time. However, it's often not, those constraints don't seem to make any difference or don't seem to be very illuminating, because the structure of the scattering amplitudes doesn't seem to tie very much or talk very much to how these constraints are. Now, this is the question of what so this is something you will see later as well. Often it's convenient in discussions of scattering amplitudes to imagine the answer to be a function of the dimension, and then change the dimension from being 3 dimensions to being some other dimension. That is not some direct experimental thing. It's taking an answer and continuing that answer as a function of d. So it doesn't mean you're going to measure that answer. What you're going to measure might be different, but it's still useful to continue that answer as a function of d. We'll see it again when we discuss loop amplitudes, and it's something that we can already think of here. That you write down some answer and then you continue it as a function of d. In particular, these processes, you could write down this field theory in higher dimensions as well, and these processes that we are looking at would take on exactly the same form in all dimensions. Okay, good. So are there any questions about Mandelstam invariance? Okay, let me just say one thing. Is there a question or? Okay, and the next topic I want to discuss is the question of probabilities and cross sections. We don't have so much time today, so I'm just going to say some simple things and then I'll stop. Yeah. Okay. You see what we've been so now I want to change gears completely. Okay, so what we've discussed today is crossing. Okay, now I want to change gears and I want to discuss a different topic. You see, what we have discussed so far are amplitudes. What we've got so far are amplitudes. Right? Right? Okay. Now there's something slightly puzzling about our amplitudes, and I want to introduce you to the problem, and then we'll discuss how to deal with it next time. Okay. All of these guys, so we might have thought, well, fine, you compute the amplitude, but in quantum mechanics, usually that's okay, right? You compute an amplitude and you square it, and you get the probability. So you might have thought, well, just square. So we are computing these amplitudes above. I had them on the board before. Just square them, we'll get a probability. Okay? But there's a problem with this. Okay? The problem with this is that m is always proportional to some number times 2 pi to the 4 times delta 4 of sum of ki. Okay? So what does it mean to square m? So m squared means it's proportional to some number squared times 2 pi to the 8 times delta 4 of sum of ki squared. Okay, which doesn't make any sense. Okay, because you're not allowed to square delta functions. Remember, what is a delta function? A delta function is a machine. You should think of it as a functional that acts on other functions. Okay, and that gives you a number. Now you can compose things, but you can't multiply a delta function pointwise. It doesn't make any sense to say this is delta of x squared. So the product of delta functions is not something that's meaningful. So to say I have delta 4 of sum of ki, I'm going to square it, that doesn't make any sense. You see this? Okay, good. There's a simple answer to the problem. There's a simple conceptual answer to the problem. You should never get confused by this fact. Okay? The answer that I'm going to give you in the next lecture is going to be slightly different, okay? Because of technical simplicity. But if you didn't care about technical simplicity and you just wanted to understand conceptually what the issue is, then the answer is very simple. Okay? We have a delta ki because our external states are not normalizable. You see this? Because the external states we are using plane wave states. Right? Okay, with various factors that depend on what normalization we're using, but we have always been using these states which are delta function normalized. Right? So the external states we have are not normalizable. So it's not surprising that we get this delta function. And why should we expect that we'll get a sensible probability when we are not using normalizable states that were normalized to start with? Our initial probabilities were not normalized to 1. So why do we expect that when we compute an S matrix, we'll get some sensible probabilities? Okay. So the conceptual point is, so conceptually, we should always do something different. Always consider some in state which looks like okay. We should always consider some wave packet which involves some integral over some wave function. You can choose that wave packet as you like. You can make it very sharply peaked if you like about a momentum, about some Gaussian. But it's important that in should be equal to 1. Okay, which puts some constraint the exact factor you get here depends on how we normalize the states. Okay, so I'll put a hash here because that factor is not important. Okay, is equal to 1. Okay, so it tells you that this psi squared with some factors that come from ki kj, when you integrate over dki has to be equal to 1. Okay. So you can choose it to be a sharply peaked, very sharply peaked Gaussian, but you can't literally choose it to be a delta function. If you did that, you would have a delta square already in the initial probability. Same way, the out state you should choose should always also be some other psi tilde of k1 to kn with the same probability, right? Out should also be equal to 1. The same property, it should be normalized correctly. So you have to smear these things a little bit. Okay. If you do this and then you compute in out, is well defined, or let's call this well defined for normalizable states. Okay, there's no problem. Because what will happen? Well, you'll take this delta function and you'll integrate it with some wave function of the initial and the final guys. You can use this delta function to do some of those integrals, but then you will not have any delta function anymore. Okay, so you will not have, so it will be perfectly finite, right? Well defined and finite. Doesn't have any delta functions. It'll just be some number. It'll be some number that will depend on what this psi is and what this psi tilde is. Is this clear? And then you can square it. Okay. Okay, so mod of s squared is also finite. Because s is finite, so you can square it. There's no problem. Okay. So this fact that you get a delta function in amplitudes is not really a problem. It has to do with the fact that we are working in this basis of plane wave states, which were not normalizable to start with. We should really have been working in the basis of normalizable states. If you work in the basis of normalizable states, you get finite S matrices, you square them, you get a finite number, you get finite probabilities, everything is finite. Okay. So this is not really a problem. Is this point clear? However, we are not going to do this in the next lecture. Why are we not going to do this? Because wave functions of these momenta or wave packets are not very nice objects to work with, right? When we work with these plane wave states, we get these nice simple amplitudes that we've been finding so far, 1 by k1 plus k2 squared. Now, if I told you, integrate that with the Gaussian e to the minus k1 minus k1 square by sigma squared, you would find that those integrals would just be a mess, right? And then you would say, why did you choose a Gaussian? I like something else. I like a sinh. So you could say something else. So there is not even a choice of what the real wave packets are, right? So we'd just be introducing a lot of parameters, and we would in defining the wave packet, and we just end up with a mess. So conceptually now, of course, that is what really happens. If you really are doing some experiment, and really there is some wave packet, you never start with exact plane waves, okay? But technically, working with the wave packets is not a good way to teach a QFT course or to do QFT calculations. So in the next lecture, I'm going to tell you how, by putting the right cutoffs, you can in fact interpret this delta 4 ki square, so that if you start talking about questions of cross sections, which is what people measure, you can make sense of what happens when you square the delta function. Okay? And the basic idea is going to be what? It's going to be, well, you think of wave packets, but then in the end, after you have computed the physical quantity, imagine that you're going back to plane waves. You're asked the right kinds of physical questions, and then you'll find you can make sense of these delta function things. Okay? However, the manipulations we'll do next time, you should remember, are just manipulations for technical convenience. Conceptually, this is never a problem because you can always think of wave packets. Okay. Okay. So last point, just to summarize what I said, I pointed out that the amplitudes we have computed have these delta functions, which suggest there might be a problem in computing probabilities. But this is a fake problem. It's occurring because we are using this for technical simplicity. Okay. So conceptually, there's no problem. But technically, there's a bit of a problem because we want to continue working with plane wave states. So we'll see how to make sense of probabilities next time. Yeah. Okay, good. So we are done. I'll stop here. Are there any questions about this last thing I said?